We start? Okay, so welcome everyone to the Friday Colloquium. So it's a real pleasure to have Kabir Ramola visiting us from the Tata Institute of Fundamental Research Center for Interdisciplinary Sciences. Kabir got his undergrad at St. Stephen's College in Delhi and then went to the Tata Institute of Fundamental Research in Bombay, where he got a PhD working with Deepak Dhar. After that, he moved to Paris for a postdoc, working with Satya Majumdar, and then he had another postdoctoral stint at Brandis, working with Bulbul Chakrabarti, and after that he's moved to TIFR as a faculty member, where he's been since 2019. So Kabir has broad interest in statistical mechanics, and I should also tell you that Kabir is going to be around for the entire week, so if you'd like to meet him or chat with him, just drop him a line or see him in his office in 403 or something, on the 4th floor. So today he'll tell us about Athermal elasticity from crystalline to amorphous packings. Thanks.
Am I audible? Yeah. Thanks a lot, Ajit, for that introduction. Today's talk is going to be on the broad topic of athermal elasticity. I think you've already heard one version of athermal elasticity from Shubhro a few weeks ago. I will be focusing more on the crystalline aspects of athermal systems and also try to make connections to amorphous systems through this talk. This work has been done with several collaborators, graduate students Pappu Acharya, Debankur Das, Roshan Maharana, and Jishnu Namputri, as well as colleagues Surajit Sengupta, Shubhro Bhattacharjee, and Bulbul Chakrabarti. So what are athermal systems? So athermal systems arise in everyday life and are ubiquitous throughout nature. Most importantly, by macroscopic particles that don't really undergo any relevant thermal fluctuations. So in usual statistical mechanics, we see that you have to move through phase space and configuration space in order for you to be able to define an ensemble, whereas in athermal systems of the kind that you can see here, pills, everyday solids, and even sand, for example, really the system is static and it is not moving through phase space as such. So the question then arises, how do you build statistical mechanical theories for such systems? Because they seem to have all the hallmarks of solids, including elasticity and including response to stresses, and they don't deform easily like a liquid, whereas in some situations they also flow. So these are some intermediate systems between solids and liquids, but clearly are very far away from the usual statistical mechanical frameworks that we know. So building theories for such systems is quite a challenge, mainly because they arise in many situations, including biological situations, and most importantly in the physics of glasses and granular systems. So much of my research in the last few years has been devoted to understanding the properties of such systems and trying to come up with theoretical techniques with which to characterize them. And one of the main ideas that I will be introducing in today's talk is elasticity of such materials and how we can go beyond linear elasticity in such materials using theoretical techniques that we've recently developed. So during this talk, I will try to keep the equations at a minimum, only keep them for the purposes of illustrating the techniques, but please feel free to stop me at any point and ask questions. Okay. So what are the features of athermal systems of the kind that I just showed you pictures of? Well, first of all, thermal fluctuations are negligible or irrelevant in the sense that the particles are so large that the ambient thermal fluctuations are very small in comparison to particle sizes, and so they don't really move in configuration space. So because of that, a usual partition function description of such systems is not a very good description, and so free energetic descriptions are also not very good. But you can still have interactions between particles governed by potential energy, and mainly the dynamics of such systems or the properties of such systems are governed by the potential landscape that is coming from the interaction between particles. So because of this, we don't have the usual phase transitions that we see in statistical mechanics, but still you can have very strange transitions where, as I showed you, sometimes the system behaves as a liquid, and sometimes it behaves as a solid, and these are governed mainly by macroscopic variables such as density and packing fraction, very similar to what we see in thermal systems, but the reason why these transitions happen are wholly different. And so these many transitions such as jamming transitions are seen in such systems, and not just that, you can also understand low temperature glasses using many of the techniques that have been developed to understand jammed systems. And so there are still many open questions in this field as to why such transitions occur and what is the true nature of them, because configuration space, as you know, is exponentially large. So really understanding the nature of motion through configuration space, or what part of configuration space is relevant to describing which system, seems to be the main question in these models or in these systems. And so developing techniques to understand such systems is an important part of this research. So before I move on to the amorphous systems that I'm talking about, I'd like to introduce again the linear elasticity framework that all of you know. The fundamental equations of static equilibrium for any system is usually given by the stress tensor. The divergence of the stress tensor is related to the external force that is applied on this. So this is an equation of force balance which is simply coming from Newton's laws, and it must be obeyed by any system that is not in motion. But the non-triviality of this framework comes in when we try to understand what the stress tensor really is, where does it come from, and what kind of stress. And that strain tensor is related to the stress tensor through linear elasticity relations. And as soon as you posit this constitutive relation between the stress and the strain tensor, which all of you are familiar with, it's a fourth rank tensor, that is the elasticity tensor, it leads to equations that form closure equations for the displacement field. So you have this stress tensor imposing the divergence-free constraint on this. And the stress tensor leads to an equation for the strain tensor from which you can derive displacement fields for the system. So if you have linear elasticity, just using these relationships, you can then solve for the displacement field. So this is very well known in most systems, but in amorphous systems, it's not clear what these displacement fields are, which I will go through in detail in the next few slides. But the elastic moduli, this fourth rank elastic modulus tensor, is governed by macroscopic properties of interactions between particles, the nature of their arrangements, and what kind of underlying microscopic disorder is put into the system determines what you have in this elasticity tensor. So this is sort of my overall summary of linear elasticity. But then the question becomes, how do you go beyond linear elasticity? And are there corrections to linear elasticity in materials which do not obey some free energetic description? And you will see that in athermal systems, really linear elasticity is obeyed for some amount, very small regions of configuration space, but in most cases you need to understand the nonlinear terms. And so in today's talk I'm going to be talking about particular methods that we have developed to understand nonlinear corrections to elasticity in an exact framework. So the next step to do linear elasticity theory in amorphous packings would be to understand how linear elasticity emerges in a disordered network. Because, as I said, it's very very much related to the underlying network, and what the linear elasticity constants are would then change quite a lot between different packings. So for example, I took a packing of this sort of just grains, and I changed, I just shook it and then I let it settle down again. You have a completely different network that has formed. So then the linear elasticity constants for that network would be very different from the previous one. And so how do you take care of such a thing? So in a disordered network, the static equilibrium conditions have to be imposed exactly at the granular scale, and what is the macroscopic static elasticity is unclear. And this is just a simple force balance equation, and this is just a torque balance equation where these are contact forces. The G stands for the grains, C stands for the contact of that grain. And so the static equilibrium conditions are imposed on the granular scale, but the particle level force moment tensor is not readily amenable to continuum treatments because of the disorder in the packing. And so it's necessary to go to coarse grain stress tensors in order to understand what is happening at large scales. I won't go into detail here. Shubhro has already explained this in quite some detail. So what happens if you include the granularity of the packings in such systems? You can see here I have two experimental images of photoelastic disks just settling under gravity, and both of them have formed disordered networks. They differ in the nature of the particles. One of them is circular and the other are hexagonal, pentagonal, and so on. But you can see very clearly that the stresses in this system are not very homogeneously distributed. So granular systems display highly inhomogeneous stress transmission properties, and it's clearly very much linked to the network that you're working with. If I was to try to model this with continuum elasticity frameworks, you would see that you would have some very nicely, smoothly varying stress field, whereas if you now try to solve this at the granular level, you will see very inhomogeneous stress distributions. So the question is, how do you actually model such a system, and what are the necessary ingredients that go into the modeling of such systems? And this is a sort of famous understanding of granular systems is that stresses propagate along force chains, which seem to be these optimal path-like structures, which the understanding of why these come about is still not very clear. But we can try to model them in certain ways. So one way to do such a thing, to understand stress propagation in granular systems, is through doing a disorder average. What I mean by that is, in statistical mechanics, you always take an average over a configuration space or some time average quantities and so on. Well, you can do something very similar in granular systems. What you can do is, here I've created a granular packing where you put some external forces at the center. Here, these three particles have an external force pointing downwards. So you're sort of pinching this configuration, and these are elastic particles made out of, you could think of some harmonically interacting particles. And you sort of counterbalance that force at the bottom here by adding forces on all of the particles along this line. And curiously, what you see is when averaged over several realizations, the stress response of such a system produces the properties that you see from linearly elastic media. That is not surprising, because when you average over disorder, you will end up with a very homogeneous kind of medium on average. So even though individual packings have very inhomogeneous stress distributions propagating through force chains, when you take a disorder average, you see linearly elastic materials that are governed by linear elasticity theory. So on the left here is the stress distribution sigma xx of this packing before adding these extra forces. So it's very, very much varying in space, and it's quite inhomogeneous. Then you add an extra force, and then you look at the difference. That's why I've said delta sigma xx, and you average over configurations. And these are results from numerics, and this would be the theoretical prediction from linear elasticity theory. And as you can see, as you average over more and more realizations, you start to see linear elasticity theory emerge. But the question then arises as to how such linear elasticity can be understood when you have contact networks that are disordered. And so much of my talk today will be trying to understand and modeling such systems using microscopic models, which are very close to crystalline systems, but have some ingredients of disorder put in, which can then be used to understand some deviations from crystalline elasticity. So yes, please, yes.
This average stress response diversity, does it depend on the shape of the particle, or is it?
In this case, because I've averaged over many configurations, the individual shapes don't seem to matter, but we haven't checked with different shaped particles, but the expectation is that it will not change. It should not.
In the sense that if they are more linear sort of a thing, if there are some kind of domains that are developing, would that change this?
Upon a very large amount of disorder average, I don't think that will. So in the sense, the domains would be averaged over when you do such a thing. So for example, in polycrystals, you would probably see very inhomogeneous stress transmission along the domain walls, but if you average over many configurations, this would probably not be true. But we haven't tested that, but the expectation is that it would be that, yeah. Yeah.
Like the snapshot, this is numerics and this is the...
So this is one snapshot of a configuration. This is the disorder average. Yeah.
What are the up and...
Yeah, sorry. So this is for XX, the XX component of the stress tensor, and this is the XY component of the stress tensor. Yeah. So, any other question? Yeah, okay. So how do you introduce microscopic disorder into models where you can then do some sort of exact calculations in order to try to understand some of these features? As I said, the stress fields of linear elasticity emerge upon disorder average, but the lack of reference configuration, and I'm sure you heard this in detail from Shubho, that the unphysicality of displacement fields, because when I do a disorder average, there is no true reference configuration from which to expand about. So if you take a linear elastic material, the epsilon ij, which I wrote down, which is, let me just go back one step. The U's, which are the displacement fields, these are the displacement fields from a reference configuration. You have a configuration which is stable, and then you perturb it, and the displacements of the particles from that reference configuration lead to some elasticity properties. But now if you do a disorder average, so suppose you take this and you do a small perturbation about this configuration, you will see this particle gets displaced a little bit, that particle gets displaced a little bit. But now if I average over many configurations, the reference configuration is lost because there is no true reference configuration. Each of them has their own different reference configuration. So the displacement fields are unphysical when you do this disorder average. So then the question becomes, where do the stress fields emerge from? Is there a stress versus strain relationship? So that is not very clear, but recent work of ours has tried to make an argument that the strain fields are actually gauge potentials and they are not physically observable. But in this talk, I'm going to try to explain different directions towards understanding such systems where you can compute the displacement field from a reference configuration and try to gradually introduce this into an amorphous state, which then loses this reference configuration. So the microscopic disorder in such systems can be considered to be of two kinds. Two broad categories. One of them is a disorder in the distances between particles. And another one is a disorder in the adjacency. So suppose some particles have 5 neighbors, some particles have 7 neighbors, and so on. So these two categories I am decoupling in order to try to make a simplistic model with which to understand such systems. So in this talk, I'm going to focus primarily on systems where the adjacency between particles remains fixed. And to do such a thing, we treat a triangular lattice of particles, of very large macroscopic particles, so they don't have thermal fluctuations, but they're made out of soft particles, and they interact through a simple spring-like potential. So this is a very paradigmatic potential for soft interactions. And here I've introduced disorder in 3 different ways. One of them is in the particle sizes. So you can have a triangular lattice of macroscopic particles made out of different sized particles, and the potential of interaction between different particles obeys this power law kind of behavior, which is sigma ij is the summation of the radii between particles. Sigma I and sigma j are the different radii of the particles I and j. And so sigma ij could be random in the sense that this particle I and j could have different radii, and so that there would be some randomness in the sigma ij, which is a summation of them. And this is and this is a one-sided interaction, so it only turns on when Rij is less than sigma ij, which means that you have an overlap between particles. And you can also introduce disorder in the stiffness between the interactions. So this Kij represents the stiffness of the springs between the two particles. Or you can also have disorder in external forces that have been placed on each particle. So this is sort of a generalized soft sphere model where you have external forces at acting on every particle, and you have different sized particles, and you also have different stiffnesses between them. But you can take different limits. And if you choose alpha, which is this power here, if it was Hertzian interactions, you'd have 5/2, but you can have harmonic interactions. And our results are not very dependent on this alpha. You can do the same techniques. And so you can have radii and spring constants that are different. And in this case, the particles can have some disorder variable introduced into the sizes. So this zeta I represents some disorder in the particle sizes. Sigma naught is the original radius. So when zeta I is all 0, then they're all the same size particles. Similarly, you can have some disorder in the spring constants. I'll focus mainly on this polydispersity, as it's known, changes in the particle sizes and diameters. And this model has actually been studied quite a lot, which is why I'm focusing on that. So in this case, if I take zeta to be uniformly distributed between minus 0.5 and plus 0.5, and eta is some strength of the disorder, so you can change this eta. The larger the eta is, the larger the variation in this particle sizes, and so that represents some polydispersity strength. Okay. So this model has been studied in detail previously, but I will just introduce some understanding of what I'm going to do next before I tell you what the results of such a model is. So if you consider a general interacting model on a triangular lattice, so these are particle positions, and as I said, I is this position of this particle and j are its neighbors, which are labeled from 0 to 5, let's say. Each particle has 6 neighbors. This is some central potential, so this is Rij is the distance between particles, so the force, so the potential only is some function of just the distance, and zeta I are the quenched variables which are representing the disorder, for example, on the particle sizes. The total energy is the sum of pairwise interactions. The interparticle forces are simply given by a derivative of this total potential, which because it's central, you get only normal forces. Forces are pointing along the direction connecting the two particles. What we need to impose at this stage is when you are at the energy minimum, or you are in a force balance or static configuration, every particle has to obey force balance. So if I take the x component of the forces acting on particle I from particle j, and sum over all j, that has to be 0. And similarly for the y component of the forces. These are the only equations that govern the static configuration. But as you will see, even solving this is quite complicated, which is basically amounts to solving 2n nonlinear equations in order to determine the positions of each particle. And this is usually done on the computer using sophisticated numerical techniques like conjugate gradient minimization or Fourier minimization. But I'm going to introduce a few techniques that you can use to actually solve these nonlinear equations hierarchically for this simple model of particles in a crystalline arrangement. So this particular model that I introduced with just particle size dispersity was has been studied quite a bit, but starting with this study into 2015, where they looked at the change in polydispersity through a large amount of variation in particle sizes. So initially when eta is 0, that is all particles are the same size, the system settles into a crystalline configuration. Every particle is in force balance with its neighbors, and all the forces between particles are equal in magnitude. And then as you increase eta, this is the sizes of the particles start to vary. Initially you have very crystalline configurations, but then the particle contacts start to break, and so the colors here represent how many neighbors each particle has. In the crystalline configuration you have 6 neighbors for each particle, and as you increase the particle sizes, the number of neighbors changes. So keep in mind that each of these configurations is in force balance. So increase some particle sizes, decrease some particle sizes, that induces some motion of particles to in the surrounding, but you have to impose force balance at every stage. So these are all energy minimized configurations. And at very large eta, lots of contacts break, and at sufficiently large eta, which is the sufficiently large polydispersity, you end up in an amorphous state. So this model is very intriguing in the sense that you can tune properties all the way from a crystal to amorphous states. So amorphous states are quite hard to characterize theoretically, but the hope is that you can try to develop techniques on this side which could lead to some understanding of what is happening near the amorphous state. And there is a transition between these two classes of configurations, which I'll describe just in a little bit. So as you increase polydispersity, contacts break. However, the crystalline order is preserved even for a large amount of polydispersity. But if you look at real space correlation functions, at least up to some small amount of polydispersity, you really cannot distinguish between these states. So if you look at, for example, psi 6 order parameters of bond orientation order parameters, you're always going to see very high ordering in the system, because the positions of the particles are changed very slightly because of this polydispersity. So they're very much in their crystalline neighborhood, but they still have very interesting properties. Any questions? Okay. So here is a phase diagram of what happens to these systems as you increase polydispersity. And so this phi minus phi Cp denotes the distance to the non-overlapping configuration. So when phi Cp represents the hard sphere packing fraction. So what you do is you overcompress the system. You have particles that are overlapping, and then you allow for some disorder. And as you increase the disorder, at some critical amount of this disorder, you see a transition from crystalline behavior to some sort of disordered crystal-like behavior. But I won't go too much into exactly what this disordered crystal phase is. But you can tune these properties all the way to this amorphous solid. And as you see here, this is a plot of the bond orientation order parameter, which doesn't change very much as you go through this transition. And this transition is characterized by some very strange hidden variables, as was described in that study, but it has some interesting properties. For example, as you increase the polydispersity, the contact numbers vary quite smoothly. This is the average coordination of the system. It starts from 6 because all particles have 6 neighbors, and then as you increase polydispersity, the number of contacts start to break, and these are for different overcompressions. So if it's very, very highly overcompressed, it takes more polydispersity for you to start breaking contacts. But this doesn't show any variation. But if you look at quantities such as this variance of the individual contact numbers over one packing, and then look at the susceptibility of that variance of contact numbers, and this is denoting disorder average over different realizations, then it seems to show some sort of phase transition-like behavior, and it's still not very well theoretically understood as to why this happens, or whether this is truly a thermodynamic transition in the sense that does this order parameter show a system size scaling? That is also not very clear, but there are interesting transitions that you can induce in such a model. Okay. So we also did simulations on such a system where we first allowed thermal fluctuations to occur in the particles, and so looked at the distribution of forces between particles. So here I've plotted the distribution of forces Fx and Fy, and the z-axis represents the histogram of forces between interparticle forces. So if it's a pure crystal with at zero temperature, with no thermal fluctuations, you will see 6 delta function peaks, which correspond to the 6 different angles of the forces. So this would represent forces along the x-axis, this would represent the other 5 directions. So you see delta function peaks. But now as you allow for thermal fluctuations to occur, you see some spread in this distribution of forces, and this thermal fluctuation does not respect force balance. So you're not imposing microscopic force balance for every configuration. They're just fluctuating about their crystalline positions. So the forces also fluctuate in this almost Gaussian manner. And as you increase temperature, this is for increasing temperature, very close to zero temperature, and as you keep increasing temperature, you see this distribution of forces. But now the question arises as to what would happen if you exactly impose force balance or static equilibrium conditions at every stage, and think of polydispersity as some temperature-like variable. And so if you do that, you average over different polydispersity realizations, you see these kind of force fluctuations. So initially you have 6 delta function peaks, but now as you increase and decrease the sizes of particles and look at the distribution of forces, you see these very remarkable linear fluctuations that occur, and at some large enough polydispersity you see this kind of force distribution. So this is quite strange in the sense that imposing microscopic force balance constrains the space of forces in which you can live on, and that seems reasonable because at the end of the day you have to impose these conditions exactly, and that imposes a huge amount of constraints in the system. So this tells you that athermal systems have very different behavior from just thermal systems, and so the idea was, can we predict such a thing analytically? And I will describe now in the next few slides techniques with which you can treat such a model and also exactly predict such force distributions, and then also try to understand some nonlinear elasticity properties of such systems. So the next few slides will have some equations, but I'll go through them quickly because this is illustrating the main idea of how to describe such systems. Yeah, please feel free to stop me at any point. But as an illustrative example, the forces between particles actually are nonlinear for the following reason. Even though I have a harmonic interaction which has this linear force in the interparticle distance, I have this pesky r hat sitting outside, which and as well as this modulus sign here. And if I actually do the I write down the forces in the Cartesian coordinates, you will see that they depend quite non-linearly on the distances between particles. Xij represents the x distance between particles I and j, Yij represents the y distance between particles I and j. So clearly the forces in the x direction and the y direction are non-linearly coupled with the displacement fields. And so in order to then add these forces and imposes the force balance constraint, I have to solve nonlinear equations. So how do you circumvent such a problem, or how do you go about solving these n-coupled nonlinear equations? The idea is simple, but the technique seems to yield some very nice results, which I will describe over the rest of this talk. What you do is you just perform a perturbation expansion away from the crystal, and with any of the microscopic disorder that you can introduce. For example, you can introduce polydispersity in particle sizes. You could have variation in the spring constants. All of them are represented by some microscopic disorder variable. In this case, I am specifically focusing on, let's say, polydispersity in particle sizes. So this variable, this is the disorder variable zeta I, which is present on every site, which could be the radius of every particle, has some expansion in some small parameter lambda, and this delta sigma I represents the change in the polydispersity or the size of the particle. And so the lambda represents a tuning parameter with which you can control the strength of the quench disorder. As a response to this, so what I mean by that is you start with a pure triangular lattice, add a little bit of variation in the particle sizes. For each amount of this variation, the particles move. But we're always going to be imposing exact force balance. So that has to be exactly imposed at every stage. So as a response to this perturbation, the positions of the particles, they were initially in the crystalline position, so these represented by Ri, the 0 represents with no disorder in the system, and there's some delta Ri that they change to, and this in turn leads to changes in interparticle forces. So if you just write it out as xi, yi, and you can then write down the changes in the interparticle forces. So the scheme seems clear. You do a perturbation expansion about the crystalline state, and you try to then find how these forces change. So the main trick is, it looks very complicated, is just do a Taylor expansion, expand the force law in terms of this disorder, where you have this change in the forces between particles I and j, x component of the force, can be Taylor expanded in the variable change in delta xij, yij, zeta ij, where xij, yij are the distances between particles, zeta ij is the summation of the two, which is, for example, the sum of the two radii, and you can just do a Taylor expansion up to any order that you like. What is crucial here is that you're Taylor expanding about the crystalline state. So because it's Taylor expanded about the crystalline state, all the coefficients in this expansion are known, and you can go to as high an order as you like. It gets much more complicated as you go further. But if this is the ansatz, which you just say that the forces can be Taylor expanded in terms of the changes in position and changes in the microscopic disorder, and they are drawn from the reference lattice, so the coefficients of this Taylor expansion are just governed by some derivatives of the potential in the crystalline state, which I won't go into. But you can then just impose force balance on every grain. But the final trick is that once you've performed this systematic expansion for the forces, you do the same expansion in terms of displacement field. So you assume that the displacement field can be written as the original, the positions of the particles can be written as some original position xi0 for the ith particle, and then some displacement fields which are order by order governed by this small tuning parameter. So suppose I want to know delta xi at order 1, this will give rise to the forces at order 1 in the expansion. So you just systematically expand the displacement fields in this fashion, do the same thing for the forces, and now if I go back one slide, you'll see, so I had this expansion given from here previously, which is the exact Taylor expansion in terms of the force of the positions, and if I'm now going to say that you can have a Taylor expansion of the forces in terms of this first order interparticle force, second order, third order, and so on, I can now take this expansion, insert it back here, and then just match terms order by order as standard perturbation theory, and end up with interparticle forces at order 1, interparticle forces at order 2, and so on and so forth. And matching terms every order, you get hierarchy of equations, which is now you can systematically and exactly understand the changes in the forces at every order. And what does that do for you? So at first order, you can write down the change in the forces simply as some first order coefficients and the change in the displacement fields at first order, and with some microscopic disorder. Whereas at second order, just matching terms, you get terms of the sort delta xij2, which is the second order change in the displacement fields, and then you will have some coupling between the first order terms, and so on and so forth. So this is a standard expansion techniques that you learn. But what you can do now is, if I was to now, I'll just go back one slide to just illustrate my point, you can impose the force balance constraints at every order. So what you can do is, if you want to solve the nonlinear equations of force balance, you can first impose it at this order, solve for the displacement fields, then solve it at this order, because that is formally still mathematically allowed, because lambda is a tuning parameter. So you can solve these at every order, and then you can basically extract solutions at every order. For example, you can impose force balance at first order, and you get this. Now you will see something very interesting. This is just now a linear set of equations. You can end up solving these equations. This can just be represented as a matrix equation. It gets even easier because we are in the crystalline positions, but you can actually get this answer very simply, and then imposing at first order leads to a unique solution at first order. Similarly, you can impose force balance at higher orders and leads to unique solutions for displacement at every order, where the lower order solutions are now acting as sources at the higher order. But it gets even simpler for us, because if I just go back one step, this equation, the coefficients are actually translationally invariant. What I mean by that is that you go to the next position, it only depends on the index j, it doesn't depend on I because it's drawn from the reference crystal. So what you can do, as is standard in condensed matter theory, is solve these equations in Fourier space. And in Fourier space, you just get a 2 cross 2 matrix to solve. And so you can simply solve for the displacement fields in Fourier space in terms of this microscopic disorder variable. And just for completeness, I've represented what these coefficients look like in Fourier space, but they're just coming from the n cross n matrix that I was talking about. And here Rj represents the fundamental lattice distances in the crystalline positions. And so therefore, this equation has related the displacement fields in Fourier space in terms of the microscopic disorder, and so then you're done. If I now write it in terms of the real space answer, you can always consider the inversion of that 2 cross 2 matrix as the Green's function. So in real space, you have the following unique solution. And keep in mind that this unique solution has already satisfied force balance. And these source terms that I'm talking about at first order would just be the disorder variables, like the Fourier transform of this disorder variable at every site, but you can do the same technique at every order and get the solutions. Okay, so that's the end of this large mathematical detour. Now I'll try to give you examples of systems in which you can use these techniques, and what can it do for you. So the Green's functions in real space look like that. The gxy and gyx are basically the same as each other, and gxx is more along the x direction, gyy is along the y direction. What does that mean? It's if I could just go back one step here, gxx represents the change in the displacement field along the x direction to some source in the x direction. So if I place some force along the x direction, how much is the displacement field along the x direction, and so on. But this represents the exact solution of the displacement fields at first order. So you can now do this for all orders. You can do it numerically, you can do it solving these equations on the computer. So what we've done here is, for example, taken a triangular lattice and placed just one particle which is larger. So what does that do? So you can just increase the size of one particle, and it changes the displacement fields away from it. From all the neighboring particles will have to move a finite distance away because one particle is larger. But because of that, it will cause all its neighbors to change a little bit. But the positions that they settle to will now have to be governed by a force law that obeys microscopic force balance. So what you can do is solve it order by order. So here's the simulation result. This is exact simulation, in the sense you take this system and go to the energy minimized configuration, which you can do using conjugate gradient. Conjugate gradient doesn't rely on any linear solving of any equations. It goes straight to the minimum of a nonlinear function. So this is the actual answer that you see on the computer, and this is what you would get from the first order theory. So what you can do now is to subtract the first order theory from the simulation, and you should then get whatever correction you get is the second order answer for a single defect. And this is what the subtraction looks like, and this is what the second order theory predicts. Again, exact. And then you can do this order by order, and you can check that this numerically converges to the exact answer. So that's one way of solving a set of nonlinear equations, although it seems very complicated. But once you formulate it in this Green's function language, you can actually solve it order by order if you need to. And so we will use this we will use this one technique to understand some corrections. So linear elasticity theory it obeys superposition principle. So if I act with some perturbation on the system and I act with another perturbation on the system, linear elasticity would predict that they would be superposable, whatever solutions of displacement fields you get. But in a system of this nature, clearly you are not going to obey superposition. So if you want to understand corrections to linear elasticity, you will have to understand corrections at nonlinear order. So this is a mathematically exact framework with which you can do that. And so I'll explain, or I'll show you some results that we have from there. But just to understand whether or not you can still get back to linear elasticity, it's not surprising that if you actually analyze the first order solutions and look at the large distance asymptotics, you will see radially, so this is the solutions for the displacement fields away from a triangular lattice of soft particles of one particle, and look at how the displacement fields away from that are are decaying, and you have this cos theta sin theta, which basically tells you that you have radially decaying displacement fields, and which you can also compute these exactly, the coefficients and so on, and this epsilon here represents the overcompression of the initial crystalline state. But the linear order displacements indeed satisfy the Cauchy-Navier equations that I posited at the beginning, and so yeah, it does satisfy linear elasticity, but the higher order terms in such an expansion are not governed by the Cauchy-Navier equation. So what do they look like? So how do you extract a nonlinear correction? Well, let's say you want to understand what the second order corrections in this theory are. You can place a single defect at the origin, which leads to the following displacement field. So here, 0 represents the position of the defect. So the delta R are the displacement fields created by this defect at 0. And so there's a delta R at order 1, delta R at order 2, and so on and so forth. A single defect placed at the position delta would also lead to some displacement fields at every order. Both defects placed together in the system would also lead to some expansion. The linear order solutions would obey superposition. So now if you subtract in this manner, if you subtract the displacement fields produced by two defects placed together in the system and subtract the individual displacement fields, you will end up, in the theoretical framework at least, with just a second order correction. But what you should notice here is on the left hand side, you can do this in simulations. This requires no theoretical perturbation expansion of any sort. You can just create a configuration with two defects and subtract the individual defect displacement fields, and whatever you get should be a correction from linear elasticity, because linear elasticity would predict that this would be exactly 0. And so using our second order theory, we've just numerically computed the source field at second order and then just inputted it and used the theoretical Green's function and just got this answer. And this is what we get from the numerics of using the exact sort of going to the minimum using conjugate gradient. And so this is basically exactly the same, and this is in log scale, by the way. So the correction is very, very tiny. It's small, but as you increase the amount of disorder in the system, this correction will also, or if you increase delta, the size of the system, of the defects, this correction will also scale. It will scale as delta sigma squared, for example. So this is a nonlinear correction that you can predict theoretically. So that's at least proof of principle that you can go beyond linear elasticity using this theoretical technique. But one thing that you can also try to understand is those very strange constraint fluctuations that I showed you for the athermal disorder. So what you can do is look at the change in the forces that occurs because of a single defect in the system. And here I've plotted the change in the forces along the lattice direction, and this is what our theoretical prediction is, because as I showed you in the first order it is almost exact, so the theoretical predictions match. But if you look at the change in the forces along the perpendicular direction, they are, this is the log by the way, they are many orders lower. So what's happening is a single defect is producing a displacement field which is radially outwards, and so most of the forces, the change in the forces are happening all along the lattice directions, and this prediction then tells you that the fluctuations of the forces along the lattice directions will be much, much larger than the fluctuations along orthogonal to the lattice directions, which you can actually use to make exact predictions for the distribution functions. So these are exact distribution functions for the distribution of forces orthonormal to the lattice directions, and this is predictions for along the lattice directions, and you will see that it's many orders smaller, but they match exactly with the linear order predictions. So you can go beyond that. You can actually try to understand how defects in such a system. So this is a crystalline material made out of soft particles, and you can see small variation in the particle sizes, and you create some bigger defects. So this is a larger defect, this is a larger defect, and here we plotted the change in the displacement field created by these defects from the crystalline position. And so the displacement fields look quite homogeneous around the defects, but now you can also ask for the question, how much energy is stored in the interactions between the particles? So if you create some larger particles, then the springs between the particles get stretched or compressed for a certain amount, and each spring or each particle now has some excess energy. And so you can now also predict the inhomogeneous distribution of energies between two defects, and it looks something like this. And I won't go into the details, but when you average over multiple realizations, that is, you place two larger defects and then you allow for small fluctuations in the background of the system, the power law interaction energy of linear elasticity theory is reproduced. So in linear elasticity theory in 2 dimensions, you expect that the energy that is stored between two defects falls off with distance as a delta to the power 4, which you can actually analytically do. So this is an analytical calculation where you can get the prefactor. But here we're showing what it looks like if you do numerics with larger number of configurations. So here you have 100 realizations of the system with two defects larger than the rest of the particles. And as you keep increasing the number of realizations, you get better and better statistics, and you start to see this power law emerging with the disorder being averaged over. And you can also predict the exact distribution functions for this energy. But what is sort of curious is that because you started from the crystalline configuration, the crystalline angles are also preserved. In an amorphous state, which is completely rotationally invariant, you will not expect that the energy of interaction, this is the distance between particles in the x direction and the y direction, the energy of interaction has a 6-fold symmetry, so they still contain the lattice symmetries. So the perturbation expansion that you do about the crystalline state still has that understanding of that it came from a reference lattice, and so there are some curiosities still to be understood there. But it's not just the system that we've introduced that has this kind of behavior. For example, there was a recent study of glasses which are very near crystalline, and they looked for, in the low temperature regime, they looked for what the distribution functions of, let's say, stress or bond orientation parameters and so on look like. And we just looked at the force distributions in this model, and it is very much like what you see in this model that I was just introducing to you. And so there are some connections to be made with glasses, because glasses at low temperatures are still governed by the constraints of mechanical equilibrium. And so there are some connections to be still made with such systems. In the next 5 minutes, I'll just quickly tell you about models of stress transmission of such athermal systems, which can be sort of amenable to the treatments that I've just described. So simple arrangements of particles in a triangular lattice have always been used to model stress transmission in such materials, and there were a whole host of studies starting from this one that have tried to model stress transmission on triangular lattices. So with the kind of interactions that I described and the kind of techniques that I was describing previously, you can make some predictions, but exactly the same sort of expansion that I described before, but instead of having just force balance on every grain, you also have global force balance, so the system doesn't accelerate. You can put external forces on the system and look for how stresses are transmitted, and you can get exact results even in this case. I will skip over that. But what you can show is that if you have uncorrelated microscopic disorder, this leads to, because you have underlying force balance constraints and much more constraints in the system, you don't have a length scale in the system. So you get long range correlations. In fact, the correlation functions scale with the system size. And you can do this for multiple cases. Here's just one configuration that I've drawn of particles in this triangular lattice arrangement, all same size particles, but now you have random forces at every point, and the colors represent the displacement fields from the crystalline position. And you can see, even though all the forces are very uncorrelated, you see these huge regions of correlations that develop, and you can then perform exact calculations of this sort that I just described, and you can see the correlation functions. And these correlation functions, they don't really have a length scale. You can show that they are exactly long ranged, and they have very strange behaviors near the small distance limit, which I'm not going to discuss at this point. But here, these are displacement correlations arising from randomness in the spring constants. So you have the configuration, and you allow for variation in the spring constants, and the displacement fields that develop due to the randomness, you can just calculate the correlation functions and measure them numerically as well. And they have this kind of symmetry. As you can see, it's larger along the 45-degree degree angle. But if you look at the randomness in particle sizes, they seem to have exactly the opposite symmetry in the other direction. Again, you can do this theoretically. And finally, you can just do the calculation for randomness in the pinning forces, and you get some other symmetry in the system. But they're all amenable to these kind of treatments that I was talking about. Similarly, now you can start to look at macroscopic properties. Knowing this perturbation expansion for where the displacement fields, what displacement fields develop as a response to macroscopic disorder, you can try to make predictions for the average coordination of the system, although you don't do very well. And the reason that you don't do very well is because then you start to break contacts in the system. And once you break contacts, you have to then treat the system differently, because the perturbation about the crystalline state assumes that the contact is not broken. So once you start to break contacts, you have to then put in exact constraints, which you can also do, but it gets more complicated. So here's some prediction just from some mean field theory for what the number of contacts would look like, but the exact, so the actual answer in the system is slightly different, and we have been investigating that recently. And I will finish this talk with a particular example that you can use such techniques for. So what you can do is try to understand the stability of these crystalline systems using these techniques. So on this square I have drawn here represents the quenched disorder in the system. So if you remember, the quenched variable is drawn from a uniform distribution between -half and +half. So this represents, the square here represents the quenched disorder in the system, let's say in 2 particles. So for quenched disorder in all the systems, it will be an n-dimensional hypercube in all the particles. But here I'm just representing it by a 2-dimensional distribution, and each point inside the square represents one particular realization of the quenched disorder. And now what you can do is, because you have an exact mapping between the quenched disorder and the displacement fields, you can then try to understand which quenched disorder leads to a violation of the overlapping constraint. And for some quenched disorder, the system violates no overlapping constraints. So 2 particles are no longer in contact. So once that happens, one of the contacts is broken. And when a contact breaks, you have some discontinuous changes, which looks like a plastic drop in the system. But you can actually predict exactly when these contact breaking events occur. And I won't go into the details, but each of these lines that I'm drawing here represents one of the contact breaking conditions between particles. And you can then ask, when do these lines sort of intersect this disorder? And all you have to do is calculate the volume of the intersection of these contact breaking conditions with the volume of this sphere, of this hypercube of quenched disorder to get the probability of the breaking of a contact for a given amount of disorder in the system. And here, just as a proof of principle, I've shown here epsilon represents the strain in the system. So what you can do is you can take this system here and you can increase the system size by a little bit and ask, by putting quenched disorder in just 2 particles, at what strain does the first contact break? So this is typically done in stability experiments in glasses and in granular materials, where you try to understand the stability of a system to external perturbations. So here you're just asking, at what strain does the first contact break? And here this is the distribution computed by using linear programming to figure out what the volume of this intersection is and so on. And these are points from exact simulations, the actual simulations of systems. So you create a system with some amount of quenched disorder, increase the strain, and ask when does the first contact breaking event occur, and the distributions match exactly. So you can then generalize this procedure to putting disorder in 3 particles, which then would represent a 3-dimensional quenched disorder space. You can put it in 4, and so on and so forth, and you can then try to understand the stability of such systems. One thing that sort of emerges from such studies is that you're very weak system size scaling of these distributions, which has been a mystery, but like with these kind of techniques, we could understand that there is some sort of logarithmic behavior, although still far from very realistic situations. These are very near crystalline and small polydispersity and so on, but you can use such techniques to understand deviations from crystalline behavior. So as a summary of this talk, the simple lattice adjacency that was created for this model allows you to extract many non-trivial exact results in such systems, and hopefully can be used to understand elasticity properties and stress transmission properties of amorphous materials, response and characteristics of sheared glasses that are governed primarily by low energy. The low energy behavior is governed mostly by their by the potential energy surface. So maybe glasses can also be described using such techniques, because at very low temperatures they're primarily governed by mechanical equilibrium conditions, and so that's a hope that we can try to use techniques for crystals to understand glasses as well. And active particles have been of much recent interest, so we are looking at how to understand correlations in active particles using such techniques. Biological tissues are, of course, one of those paradigmatic systems that should be amenable to treatments of this sort, and because they are also fundamentally athermal in their nature, and what kind of elasticity properties emerge in such tissues would also be an interesting direction. And finally, the million-dollar question is, where do the timescales in all these systems emerge from? So I've not touched upon this at all, but this is really one of the big questions in this field, where you have static configurations, but going from one static configuration to the next static configuration requires dynamical motion through phase space. So what governs this motion, and what trajectories does the system take through phase space, and how important are static conditions in near this mechanical equilibrium condition leads to, and how does that lead to timescales, is something that would be interesting to understand, although I haven't touched upon it in this talk. And with that, yeah, I'd like to take questions. Yeah.
How does that match with these predictions?
So,
you can expand any order you wish.
But so nonlinear, you mean by like viscoelastic materials and so on? No.
For that deviation.
So I haven't tested that. So that's something that would. I don't know if that would predict, let's say, higher order corrections of this nature, but that's something I should explore. I haven't. Yeah.
The other one was, suppose I have in engineering thing, two things mixed together to form something, and then you want to find the behavior, macroscopic behavior of that. There is something called rule of mixtures, where you just sort of average out the area, and that seems to work very well. So, and that polydispersity is like many things mixed together. So does it match with the rule of mixtures or not? That is the other one.
That is another thing that I don't really know the answer to. But so if you have, let's say, bidispersity, then this linear theory would predict some sort of superposition, which could lead to a rule of mixtures of this sort. But I have to check that. But that's an interesting direction to check. Sorry. So if I go back here, yeah.
If I had one more question.
Yeah, please.
How would the introducing disorder in the, let us say, in polydispersity affect the fracture properties, for example?
Yeah, so that's a very, very interesting question. So this is actually related to what we're studying here in the stability criterion here. So I have not plotted it here, but as you increase the polydispersity, so this is just introducing polydispersity here. So this is like a fracture property. This is the breaking of a contact. This is a global property of the system. This is like a fracture, but not a crack propagation. It's just one contact breaking. But once one contact breaks, the system is more amenable to other contact breaking events. So this is indicative of when a fracture would occur. But as you increase polydispersity, you get a larger distribution here.
No, so, this is more like, some activity in the system, not fracture as such. So if I shear a glassy material or something, things slip. This is more indicative of, is it indicative of that or the system failing? Which one is this?
So this does look like a system spanning event that occurs. So it's not a localized event. It's a system spanning event, but it would not be considered to be a failure in the sense of a fracture. Yeah, but I would expect that as you increase the polydispersity, the distribution of when this fracture occurs would also increase, and the scaling can also be extracted from these methods, although the exact distributions will be very hard.
When you do this perturbation expansion of your forces and all,
Yeah.
so usually perturbation series is always very ill-defined. It is an asymptotic series. So what ensures here that it works so well here?
Yeah, so again, when this parameter is small, it converges. But you can actually write down criteria, for example, when the second order term becomes larger than the first order term, then you don't have a very good convergence. But radius of convergence of this expansion remains to be studied. In fact, that's a very interesting point because at some, let me just go back here, at some amount of disorder, which is eta here, you should lose all properties of the crystalline state. So as I showed you, you end up with crystalline symmetries even in the interaction energy at small polydispersities. So at some point, when you get to this amorphous solid, which is completely rotationally invariant, if you look at this configuration, you should not be able to see which reference structure the crystal came from. But that seems to be preserved even beyond this disordered crystal transition. What do I mean by that? I go here and show you the force distribution. This is a very large eta. And you still have this 6-fold symmetry. And so much beyond this transition, this perturbation expansion or the crystalline state is still preserved. The memory of the crystalline state is preserved. So I would expect that somewhere here it should break down. But where it breaks down is a good question. But the radius of convergence is, not limited. As long as it's small, then of course each term is much, much smaller. So you can.
What decides the radius of convergence? This is not some kind of phase transition. So you have some kind of correlation function diverging or.
That's also not clear at this point, because what really you must do is solve it order by order and then check the magnitude of the second order term. So it's not simply that you can, so let me just go here. You cannot just simply extract the second order displacement field without solving the first order terms. So there might be some bounds that you can put, but I haven't worked that out. But yeah, it's sufficiently complicated. Even the source terms at second order are complicated enough that I don't know the answer to that actually. But it remains to be tested,
I have a more naive question.
Yeah,
we were talking about phase transitions in this context. So how do you characterize the phase transitions?
So it's a good question. So typically what you would do is, so let me just go here. So this is one way of characterizing. So you look at one macroscopic parameter that doesn't vary. For example, like in thermodynamics, you have temperature. But here you'll have polydispersity eta. Choose a polydispersity and then look at several realizations. So in the statistical mechanical sense, you have multiple configurations consistent with a macro state. And here eta would represent a macroscopic variable. And these are fluctuations or these are susceptibilities as averaged over realizations. So that is why I define it as that is why it looks like one of those parameters that you have as a phase transition. But even more directly, you can define a phase transition as follows. You can ask, is this flowing or is it jammed? Now that is a direct measure, a discontinuous change in, let's say, in the dynamical properties of the system. So if I close this point here, which is some sort of control parameter, none of these particles move. If I open it, they move. So then that's a clear discontinuous change as you tune a parameter in the system. By the size of the hole that is allowed, you have a discontinuous change in the dynamics of the system. So that is also a phase transition. but not in the same manner that you would describe, let's say, magnetic phase transition.
Do you also study volume scaling here? It doesn't make sense here, right? Because
you do study system size scaling in such systems, but it's not clear that you have any of the same critical exponents, or whether they are related to fluctuations and the correlation length. That's also not clear. It's not the same kind of scaling that you would put in. Yeah.
thanks.
Are there any other questions?
Hi, when there is a single defect within the system, then is there a characteristic size above which the role of the defect is observed? Like, since it's a larger particle, how large it has to be?
Yeah, so this is another good question. Let me just point out that these techniques that I'm describing, at each order, okay, so let me go back here. So these are all proportional to the size of the microscopic disorder. So for example, this effect that you're describing here at the first order is proportional to the size of the defect. This effect here is proportional to delta sigma, which is the change, delta sigma squared, and so on and so forth. So so the first order effect is proportional to delta sigma. So this effect will occur at any small amount of size change, but this will scale linearly, this will scale as a second order effect. So it depends on the resolution. So whether or not it becomes important is whether or not you can actually detect it. So if the resolution of your experiments is large enough, fine enough, then you will detect it, even if it's a small change. Yeah.
So I don't see any more questions. Okay, so if there are no more questions, let's thank Kabir once again, and there'll be tea, coffee outside for which you can join us. Thanks.